Welcome to the Communication Systems playlist. Today in this lecture we are going to discuss the pulse width modulation as well as the pulse position modulation. That is the basic form of the sampling and quantization. So in this lecture the title is pulse width and pulse position modulation. So it means that we are going to discuss both techniques in this first lecture. So the first one is the pulse width modulation. So pulse width modulation is very important and it is mainly used in many applications. Like it is used to control analog devices and mainly the power which is delivered to the analog devices is controlled by pulse width modulation. Its efficiency is very high, so the low power loss and precisely control the power. The application of the pulse width modulation is the example is that you can use it in dimming the LED light. You can use it in controlling the speed, fan speed of CPU. It can be used in another application, that is brightness of the laptop screen, and it is also extensively used in power electronics. For example, how does it work? So suppose we have input and then there is a switch and then we can have the output. So the control signal is also at the input of the switch. The first example was how to control the LED light. So this is the circuit, like we have a 9-volt input supply and then this is a switch, a resistor and LED, and through this switch a control signal is applied. So if the switch is open, so it means that the circuit or the LED is isolated from the supply. But if the switch is closed, so if the switch is closed or the switch is open, it depends on the control signal. Like the control signal, how it controls the on and off condition of this switch. Like the switch on and off very rapidly depending on the control speed. So like this is the square wave of 9 volts suppose. So this is the square wave of 9 volt. So if we apply 50% duty cycle, 50% duty cycle means that we can have the average volt of 4.5 volt average most of the like mostly at the LED. So it means that 50% the LED is on and 50% the LED remains off. Secondly, we can have 25% duty cycle. So for 25% means that the average voltage is 2.25 volt. So it means that the LED remains on for 25% and remains off for 75%. So it looks like that you are controlling the on and off of the LED by controlling the pulse width using the pulse width modulation. So you are controlling the on and off of LED by giving a certain amount of input voltage. It means that you are basically controlling the brightness, because if the LED remains off for more of the time, so brightness will be more. If the LED remains off for less time, so it means that the brightness will be less. So in another way, you are basically controlling the brightness of the LED. That was the first application of pulse width modulation. It also has some factors. So first one is the switching factor, like how fast the switch is on and off, and the second one is the duty cycle, which is a ratio of the time when the switch is on to the total time. Like you can say what fraction of time the pulse remains on, so that is known as a duty cycle. So let's start the working of the pulse width modulation, like how the pulse width or what is the pulse width circuit. So suppose we have that circuit, a comparator circuit. The diagram of the comparator is that one, that we are giving input at the positive terminal of the comparator, the modulating signal M of t, and then we are giving negative at the negative terminal of the comparator, the CT or sawtooth waveform. So this is like the sawtooth waveform, and at the output we are getting pulse width modulation. So and what is the condition? If the amplitude of the modulating signal is greater than the CT is greater than the sawtooth generator pulse, then the output will be positive. But if MT is less than CT, then the output will be negative. So this is the phenomena. So let's see a graph. Let's see a graph of that circuit. So suppose this black color is a sawtooth waveform. So this black color is a sawtooth waveform, and this red color is the modulating signal. So this red is MT and this black is CT. And then I am drawing the trajectory, like, so when it cut at that point, the trajectory is there, and then from this point the trajectory is there. So the red is cutting at the black, then I am drawing the trajectory there. I am drawing the trajectory there. Similarly, the trajectory here, and then all these trajectory I draw for these two combined point. So at first point, so this is the point. So at this point, so before that point, you can see the MT is bigger. So MT is bigger than CT. So if MT is bigger than CT, like at this position, before that, at this position, MT is bigger than CT. So if MT is bigger than CT, then the output is positive. But after that, here, from here, you can see CT is bigger, but CT is bigger, but MT is lower than CT. So it means that the output is negative. So similarly, at this position, MT is bigger than CT. So it means that we can have positive output from here to there. So that is why we are having positive output. And after that, from here to there, CT is bigger than MT. So we have a negative output. And then from here to there, MT is bigger, then we have a positive output, and so on, that we are getting this type of waveform at the output of the comparator. So you can see here, like when the modulating signal is negative, the pulse width is like you have a less pulse width. But when the modulating signal is positive, the pulse width of the positive pulses is bigger. Similarly, here the pulse width of the negative pulses is bigger, and here the pulse width of the negative pulses is the pulse width is less than the positive pulse width. So positive pulse width is bigger, the positive pulse width is not bigger. So this is known as the pulse width generation. So which is based on the size or on the amplitude of MT. So if MT is bigger, then we can have positive output. If MT is less than CT, then we have a negative output. So here you can see we can have positive waveform and the negative waveform, but we can have only the positive waveform and then the zero waveform here. Like if you use clamper, like at the output, if you use a clamper circuit, so if you use clamper circuit, so it will clamp out the negative portion, and then you can have only the 0 and the positive. So 0 and the positive here, 0 and the positive there, so 0 and positive there, so 0 positive there, so there, so 0 positive there. So if you are using clamper at the output at this point, like if you are using clamper at this point, so your level, like your level is from 0 to positive value, from 0 to positive value. So the second type was pulse position modulation. So using the same circuit, we can introduce the pulse position modulation. Only the additional circuit is the monostable circuit. If at the output of the clamper, if we use monostable circuit, what is the function of the monostable circuit? The function of the monostable circuit is to generate pulses of fixed duration. So it will generate the pulses of fixed duration. So you see, when it is positive, so it generates pulse here. So when it is negative, no pulse. So when it is positive, it generates pulse a fixed width. So the width is fixed. You can say fixed pulse width. So the pulse width is fixed. So when it has a signal, it will generate a pulse width of fixed width. Similarly, when it is positive, you have a pulse. 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 So you can see that the position of the pulses, before the position was here, the position was here, now the position has been shifted. The position has been shifted from here to there. So that is why you can say, by using the monostable circuit, you can generate the pulse position modulation. So similarly, we can say that the pulse position modulation, you need extra circuit, which is the monostable circuit. There are many advantages of pulse position modulation. The first one is less affected by noise. The second is noise contaminated signal can be reconstructed. The third one, transmit power is constant. And also there are disadvantage, means for this type of modulation you need synchronous circuit. So for a perfect demodulation, so if you need additional synchronous circuit, so it means that it will increase the cost as well. This second disadvantage is that the bandwidth, for this it need high bandwidth, so high bandwidth requirement. So these are the disadvantage of the pulse position modulation. So I hope you understand today's lecture about the pulse width and the pulse position modulation. So if you still have any question, so you are most welcome. You can write the question in the comment box and we will try our best to answer the question. Thank you for watching the video.